starting the next topic here. We're going to go a little bit more on the practical side. So now that you understand how calculations work, we're going to review some practical transmission lines, and I'll try to convey some of the experience working with them. And so what is good, what's bad, what you should be careful about, what some possible traps are, and basically go from there. And we're going to start with our good old microstrip line. This is the line that I briefly mentioned before, and I have actually put here its main schematic, its main geometry. So if you look at this, it's a very simple line. In fact, it's loved for its simplicity. It's literally just one strip on top of a ground plane. And that dielectric that you have below is basically the substrate that is essentially holding that strip. The picture here on the right is basically giving you a rough idea of how the electromagnetic fields look like in this transmission line. And I'm telling you that this is a rough idea because this is a low frequency approximation, and as we're going to see later on, things can get a little bit uglier when the frequency becomes higher. But by and large, what that figure basically shows you is that you do have some current that flows in the center conductor or the strip of the microstrip line. Of course, the reverse current flows in the ground plane. And then you have the electric and the magnetic field. So here you can see the electric field lines. And as we discussed before, some of those field lines are inside the dielectric, and some of them are outside. In this particular example, we actually have a passivation layer, which is relatively common in some frequencies, in some applications, where you're trying to protect the transmission line from any other external effects, perhaps, for example, humidity or exposure to dust. And in that case, some of the fields now are basically inside the passivation layer. But one thing that you should remember here is the majority of the field is actually inside the dielectric. And then you have the magnetic field as well, which is shown right here, which is basically all over the place. And that's essentially the main configuration that you should remember in terms of E and H for this microstrip line. Now, there are some serious implications because of those fields, which we will discuss as we go on. One way that I mentioned last time in terms of how we can perhaps analyze this transmission line is to essentially assume that there is an artificial medium called effective medium, where primarily has a dielectric constant of epsilon effective. That dielectric constant is between epsilon naught, the air dielectric, and between the epsilon of the substrate. And as I mentioned before, as a very first order, or probably zeroth order approximation, you can average the two to get roughly what that number might be. But essentially, the usefulness of that approximation is that now you have a uniform medium, and the electric field is inside that medium. And so when you basically make this type of an approximation, you assume now that the electric field propagates with a velocity which is equal to the velocity of light by square root of epsilon effective, and that we can basically now start having some understanding of how fast waves go, what's the phase velocity, and so on and so forth. Now, one of the interesting things that happens in real life is that there is a need to ground the line. So there is a need, in other words, to introduce a short circuit. So when you have to introduce a short circuit, what you really have to do is essentially make what we know as a via hole. That essentially means drill the dielectric, either mechanically or with laser or some type of an etching, and then fill this hole with some type of a metal in order to connect the strip to the ground. Even though actually this sounds like a relatively simple thing to say, in real life it's actually costly, and we don't like doing that. So as much as possible, we actually do try to avoid shorts in microstrip transmission lines. And in fact, the need to drill the dielectric is one of the drawbacks of the transmission line. It's a costly process. The other reason that we don't like this is that this one has some finite length, which is essentially equal to the thickness of the dielectric H, which means that you have some type of an inductance here, the effective inductance due to the length of this via hole. And if you imagine, let's say that you have a dielectric that maybe it's 0.5 millimeter to 1 millimeter thick, which is pretty common in real life, then you can imagine that now you don't really have a short circuit, but you have an inductor that has a length of 1 millimeter. and that is not negligible, particularly if you start talking about frequencies that are actually above 10 gigahertz. So this type of effects cannot be ignored really for high frequency applications. So that's one of the drawbacks that we do have on transmission line, on the microstrip transmission line. A second drawback, which we will come back to it later on, is actually related to the effect I just described here. The fact that in real life you don't have a uniform medium, but rather you have a non-uniform medium where the electric field exists, essentially introduces what's known as dispersion. So dispersion is essentially an effect that allows different plane waves or different waves to propagate at different velocities. So a frequency, for example, of 10 gigahertz will have a different propagation velocity than a frequency of 1. And that means now that if you make a pulse at the beginning of the line and this pulse propagates through the line, this pulse obviously contains multiple frequencies, and for that reason at the end of the line there will actually be dispersion, which means that the pulse will actually be wider. And so why that is an issue? Well, that's an issue because you're not really sending one pulse. In real life, you're sending multiple pulses, one after the other. And so if those pulses are too close to each other, then at the end, you're actually going to get a blurry picture, which essentially means that the receiver will get something ugly like this. And you start having intersymbol interference, you start having bit error rates, and so on and so forth. And of course, the narrower the pulse, meaning the more bandwidth you try to compress, the worse the effect will become. And the dispersion essentially limits how many bits per second you can send through this transmission line. So that's the second drawback of having this type of non-uniform electric field distribution. Now, what are some common substrates that we use for this type of lines? This is a table that shows you many different possibilities. I want to mostly emphasize a couple of effects here. So one of the main limitations when we make circuits with transmission line is obviously the cost. So we try to pick substrates with low cost. A very famous low-cost substrate is the FR4, which is used primarily for many low-frequency applications. It's one of the lowest substrates, lower-cost substrates you can choose, but it has the drawback of loss. This column here gives you the loss tangent, meaning the dielectric loss of the substrate, which is not a big deal for low-frequency applications, since the dielectric loss is not dominant in low frequencies. In low frequencies, we mostly have metallic loss, ohmic loss. But in high-frequency applications, the dielectric loss becomes an issue, and that means that not only you want low cost, but you want low loss as well. And usually those things don't go together. So usually when we look for higher frequency applications, FR4 is not a good choice. And so we will go for other substrates. Duroids are essentially one interesting choice. We will also a lot of times go for fused silica or quartz. And again, what's the penalty there? The penalty is that those are higher cost substrates, but clearly they win dramatically on the loss, particularly quartz. So fused silica is actually one of the lowest loss substrates you can ever hope to get, and that's why it's used in many high frequency applications. And by high frequency, I mean, tens of gigahertz, perhaps even 100 gigahertz. The other issue is essentially related to the size of the circuit. So when we're talking about the size of the circuits, primarily we're looking into epsilon r. Why? Because the larger the epsilon r, the smaller the size of the circuit will end up being, right? Because you're basically having a wavelength divided by a square root of epsilon r, that will basically give you the wavelength of the circuit. So when you make a quarter wavelength transmission line in a dielectric that has essentially, let's say, alumina with an epsilon r of 10, will actually be much smaller than if you make it, let's say, on polyamide with a dielectric constant of 3.2. And so everybody loves small circuits, and that means that everybody will try, in theory, to go for a large epsilon r. The problem is that usually substrates that have a higher epsilon r end up having a higher loss too, and worse dispersion as well, because now the difference between the air dielectric and the epsilon r dielectric is actually much, much higher. So you suffer higher dispersion, depending, of course, on the design, and you suffer higher loss typically. So all of these are trade-offs that essentially won't give you a clear-cut case. It will depend dramatically on which application, but these are probably three of the most common criteria that we use when we choose what substrate do I want for my transmission line.